So I would like to start by thanking the organizers for giving me this, opportunity to present the work that we are doing for, some time. Today I'll be telling you about this bulk photovoltaic effect that we see in WS2 spiral systems. So before that, this is the group that actually they are doing all the work, and I'll be presenting Megastri's work today primarily. Some of my students are here, so they'll be presenting posters. If you're interested, you're invited to visit them. So before going to the actual talk, I will just highlight what we do in our group. So basically work on confined materials, and we are mainly interested in the optoelectronic properties of two-dimensional material or their heterostructures. We are primarily studying the optoelectronic properties by changing various stimuli, but just to be self-sufficient, we mostly grow our samples, and then we do the device fabrication because we need to do the electronic transport. And in the application side, we do work a little bit on the memory stirrers and ultra-sensitive sensor platforms. These sensor platforms are mainly on the optical based. And to support our experiment, we do a little bit of instrumentation. So these are the things that we have made so far. Deepak will be presenting a poster on our very recent setup that we are trying to make, and these two are still coming up. So the research in two dimensions, I can, it's mainly we are trying to understand how properties changes as you, tune this defect, dielectric or strain. And, we grow our samples mainly using chemical vapor deposition. And in 2D, we are mainly focusing on the TMDs, WS2, WS2, MOS2, MOS2, this kind of materials. A part of our research also involves in high mobility materials. These are mainly bismuth oxyselenide and tellurine we are dealing with. And on the application side, we are working on CSPB BR3. We study their growth and their some applications in optoelectronics. We also try to see how we can use the hybrid structures, mainly 2D, and combining these 2D materials with other dimensional, basically mixed dimensional van der Waals heterostructures, and study the neuromorphic properties. And a small part of our work also involves in nanoparticle based sensors. So in growth, we found a growth promoter a couple of years back, and we got a patent on that, and it's a very good one. It can, we can easily grow this MOS2, WS2, WAC2, MOSC2, and the quality is very good. I mean, we are still growing using that, growth promoter itself. So we do believe on our research. Recently, we came up with a transfer technique because unlike graphene, the CVD grown TMDs are difficult to transfer from one substrate to another substrate. So we came up with a HBN assisted and some inclined substrate technique where we can easily transfer them and make a very clean interface. So we call it as a kind of bubble-free interface, and we can encapsulate them with the HBN on both sides. So this is the optical image, and if you do the KPFM mapping, you can see that they are underneath. In dielectric engineering, we have shown that by combining a 2D material with a 3D and then tuning their local dielectric environment, you can tune their optoelectronic property, you can improve their photo response by several orders of magnitude. We are able to improve it 3 orders of magnitude over a large wavelength range. We also showed earlier that by tuning the substrate, basically by doing the dielectric engineering, you can tune the exciter to try-on ratio in a WS2 samples. And very recently, we showed that again by using a different kind of substrate where this, it's basically pillar geometry. The pillars are 50 nanometers apart. If you place WAC2 monolayer, then you can kind of harvest this dark exciton over a large area. Strain is another interesting, degrees of freedom here. First thing that can come to your mind is applying strain by placing it on a flexible substrate and then bending it. But for doing the electrical transport properties, it's actually a little bit tricky. But anyway, we are able to make device on that, and we showed that yes, if you apply strain, then you can activate the defects, and defects can easily migrate above a certain strain threshold. There is another easier way to applying strain. You can place them on this textured substrate and you can apply strain on a nanometer length scale, like few tens of nanometer length scale. And we showed that, okay, by placing a WS2 layer, monolayer on top of this kind of substrate, you can brighten the momentum forbidden dark exciton. Another simple way to apply strain is to roll these monolayers. So here we showed that by rolling these monolayers, you can again tune their optoelectronic properties and they can serve as a better field effect transistor, photodetectors, so their mobility also improves. In the defect engineering, we showed that in case of MOS2, instead of taking this conventional MO3 as the precursor, if you take oxidized MO foil, then you can get some very high mobility MOS2 samples. Here the mobility reaches up to 100 at room temperature, which is actually pretty high in terms of the CVT grown sample. And what we found that through detailed study that in these samples there are abundance of double sulfur vacancies, which are lying very close to the conduction band, and as a result you get very high mobility, and you can see that you can even see the phonon limited mobility in these kind of samples. Whereas the MO3 grown samples, they don't show those kind of behavior. In another work, we showed that by using a low power argon plasma, you can create sulfur vacancies, and those samples are good for memory strip application. They are actually the performance, memory strip performance improves significantly. And very recently, we figured out a way to dope copper in these MOS2 samples. It's called a morphotaxial doping. So it basically keeps the structure same and replaces some MO atom using copper, and that improves the photoresponse property significantly. We are actually now using them for the memory strip application, and they are very interesting. They shows very promising result in terms of the memory strip application. And this is on the high mobility side, bismuth oxycylinder. I won't tell much about it. Vinas will be presenting a poster on this, and tailoring work. Pawan will be presenting a poster on the tailoring work. Again, these are mainly for the high mobility applications. And on the CSPB VR3, it's again on the application side, we figured out a way to grow these nanoplatelets of CSPB VR3, which are pretty long, a couple of tens of micrometer long. They are not monolayer, they are not very thin, like the thickness ranges in the range of hundreds of nanometer. But interestingly, what we found that they are very pure. Okay, they are single crystalline. So the growth itself is interesting. We got a patent on that growth. But the problem with this material is that they are water soluble. So the moment you try to do especially photolithography, then they get dissolved. So we figured out a way to kind of a modified photolithography technique to make the electrical devices on that, which you'll find in this manuscript. Interestingly, these samples, as they are very pure, they show very low dark current, and they show ferroelectricity, which is kind of very interesting, because earlier ferroelectricity was observed only in less than 10 nanometer or around 10 nanometer diameter nanocrystals, not in a bigger sample. And the Curie temperature is around 90 degrees Celsius. They also host this ferroelectric bubble domain. And very recently, we showed that this material, there is simultaneous presence of high energy and Raza excitons, and which accompanied by their distinct phonon replicas. The paper is just out. And this is in a nanoparticle fabrication using a confined geometry. I will not go in details into that. We just got a patent on that also. So for the today's talk, I will be mainly telling you about the bulk photovoltaic effect in spiral WS2. So I will try to motivate you and tell you about a bit of the mechanism, and then how we synthesize the sample, what are the characterization techniques that we use, how we figure out the symmetry breaking of this spiral WS2 sample, and then present the photovoltaic results, and what is the dominant mechanism that we are kind of expecting or suspecting. Okay, and finally I will conclude my talk. So when you shine light on a material, there can be various physical pathways. The conductivity can change. The first thing that can come to your mind is the photoconductive effect. So in absence of light, you have low current, and presence of light, the current increases, conductivity increases. But You should notice that the IV characteristics in presence of light passes through the origin. That means zero current at zero voltage. So you'll get current only when you applied voltage in this kind of photoconductive effect. And the most popular effect is the PN junction, where you have this is a photovoltaic effect. So you need a junction for that. It can be PN junction, Schottky junction, or any kind of junction where you have a inbuilt electric field which is responsible for separating this photo-generated charge carriers. So they will drive them in these contacts, and they will drive some current. And the hallmark is that at zero applied bias, you will get some current that is known as the short circuit current, and you also get some VOC. Okay, open circuit voltage, and this is for the kind of heart of all the solar cells and other things. But here you need a junction for that. And in this kind of case, the bulk photovoltaic effect, you will find the some photocurrent even in absence of any applied bias, and you don't need any junction in this case. And this is generally happens in case of inversion symmetry broken sample. So all these things, they have a different type of IV characteristics. You can see that here it is linear. Okay, generally it is linear. Sometimes we saw that in certain samples it also gives some sort of non-linearity, not too much. Okay, and it also has a VOC, another thing. They have different temporal response. Okay, they respond differently in terms of the when light is polarized, you change the polarization of the light. So you can kind of give little bit more details on that, but I will not go into that. They have a different time scale also for the response if you shine on and off the light. And so this is again the photovoltaic effect. In bulk photovoltaic effect, the interesting thing is that there is a kind of physical shift of this electron when it goes from the conduction band to valence band. I will come into that, and it has a strong polarization dependence. So let's try to see what is so special about this bulk photovoltaic effect, why we are interesting. So we can get a DC photocurrent in this non-centrosymmetric material without any PN junction, and not having a PN junction helps you to miniaturize the system. You can make a very small, tiny device, and you can still get photocurrent out of it or photovoltage when you shine light. And it is not limited by the little balance, which is the case for the PN junction type of things. The Shockley-Coulson limit is there, which tells you that silicon solar cell or other single junction solar cell will have this maximum efficiency. It cannot go beyond that. And the photovoltage, it's not related to the band gap because it really, the mechanism is completely different. It's a pure quantum mechanical origin. So it's not limited by the band gap. People have already observed, a couple of tens of volt VOC in certain material. Okay, and you can see it even a very thin layer of material. That's why it is kind of, attaining so much of interest these days. People have observed it in these ultra thin materials, in two-dimensional materials and other things. So the mechanism is basically the shift current. It's a real space displacement of the electron when it gets excited from the conduction band to valence band. Okay, and as the carrier separation happens just during the photoexcitation, so it bypasses all the problems of diffusive transport or other related scattering and other things. Okay, let's go a little faster. So people have observed, or they're trying to get this bulk photovoltaic effect in engineered 2D materials, and the way they are generally breaking this inversion symmetry is by applying strain. However, it's a bit difficult to control the strain, it's difficult to scale up, it's difficult to miniaturize. So all these problems are there. So what we thought that, okay, can we introduce a defect during the growth and try to break the inversion symmetry in this sample? So we kind of, take the help of screw dislocation. So we grow CVD, we grow the WS to spiral sample using CVD, where we have these screw dislocations, and these screw dislocations inherently break this inversion symmetry and gives rise to this bulk photovoltaic effect. So now we kind of got rid of all this, or at least some of the problems. You can miniaturize the device. Okay, it's very stable. It's easy to fabricate device out of that. So again, the samples are grown using chemical vapor deposition, By tuning the parameters, you can get this spirals of geometry, and the samples, if you optimize them, you can get a pretty big sample. Like we got even more than hundreds of micron sample. Here are some ACM and FM images. So by the way, this work is a collaboration with a lot of people. So like this cross-sectional TM is done with Pavan Nukala of IISc. So here you see that we have done the AFM, and the steps are really monolayer, 0.8 nanometer step height. And if you see that they are exactly parallel, at least in the AFM image, you can see that they are parallel. So they are not really a twisted spiral; they are still kind of stacking, but they grow using this screw dislocations. So this is kind of the first indication that they are not really twisted. We will see some other experimental observations which supports this thing. We try to, then what we did, as usual, we will first do the Raman spectra of that. Room temperature Raman showed almost similar thing as a kind of few layer WS2 sample shows. However, the low temperature Raman shows that this A1G peak and the E2G peak, they are splitted. Okay, so they are splitted in this E plus, E minus, and E1G peak is split into A1 and A2. Now, the splitting of this Raman peak can come due to this, interlayer interactions, because these are few layer samples. These are not monolayer. That's a spiral geometry. But other thing is that the splitting. So the interlayer interaction that is known as the Davidov splitting. Okay, it can split both A and E2G peak. Other thing is that it can be due to the strain. Okay, if you apply strain, then strain can also split these peaks. Now this A1G mode, which is basically an out of plane mode, it is a bit insensitive to the in plane anisotropic strain. So the effect should be less on that. However, if we measure that, then what we see that the splitting is a bit higher in A1G rather than E2GP. So we can at least kind of say that maybe there is something else. It's not something else. Maybe the strain is not the whole reason for this splitting. Probably Davidov splitting is more dominant in this sample, but still nothing is very conclusive. So then we move to the next experiment. So we did the second harmonic analysis of this sample. We did a thorough measurement, and then again with collaboration with our one of our collaborators in Poland. So what we found here that with increasing thickness, the signal is increasing. So basically, there is a constructive interference that's increasing the intensity of the second harmonic signal. And if you increase the power, you see this almost quadratic dependence, which says that yes, it is the second order nonlinearity is there. Okay, somehow this thing is not working. But anyway. So we did the mapping. There is a video which is not running anyway. What we see is that the second harmonic signal we get from the entire flake. So it's not locally broken here and there. It is everywhere present. So the symmetry is broken globally in this sample. Then we did a polarization dependent SSG analysis on a device. So this is basically the sample where these two regions are the electrical leads, and we did the polarization dependent SSG measurement on the entire sample. So these are basically the grids. At each point we did the polarization dependent measurement. Here also we saw that with the increasing number of layer, it changes quadratically. Okay. Now when we take this polar plot along this L line and we plotted the co and cross SIG, what you see that there is a 6-lobe pattern is present in that, and the lobes, they are not changing their direction. So the orientation remains fixed, but the lobe size may be changing. That I will clarify in the next slide. Which we found that it's interesting, and it's kind of also matches with our AFM measurement, which shows that they are almost in the same direction. There is no twist among that. So this also suggests that okay, the crystal orientation remains same throughout the entire flake. However, in certain places, you are supposed to see this 6-lobe pattern, which are symmetric, but in some places you do see that the lobes are not exactly same in size. So that means there is some additional, symmetry breaking thing is present, which is removing this 6-lobe pattern, which is kind of reducing the 6-lobe symmetry here. So if there is no strain present, then you are supposed to see this 6 slope thing. But as in presence of strain or something, the intensity will change like this. Where B portion is responsible for this anisotropic strain. This now it is not symmetric, so EXX is not EYY, and that disrupts the in-plane symmetry, rotational symmetry. So, and also theta is the strain angle. So, what the students did, they extracted the A, B and theta parameters. So, if you plot them, what you can notice is that if you first look at the A and B parameter, the A parameter, the range goes up to 1000, where it is in the hundreds of range. So, definitely the B is quite less, and also if you look at, notice the theta. Okay, there is some pattern somewhere, but it is not really showing some preferential, orientation across the entire spiral. So what we can kind of, claim here that the symmetry that is broken is mainly due to the inversion symmetry, and maybe there are some local rotations which reduces the, symmetry further in certain places, but there is no systematic thing. We really don't see a two dumbbell kind of thing where the entire rotational symmetry is gone. Okay, so main thing is probably the main symmetry breaking thing is the screw dislocations in this case. Then we made finally now we come to the device. Okay, we made the device and then we measured their electrical properties. Okay, we do see the zero bias current when you shine light. So this is in presence of dark and this is when you shine light. We made multiple devices and see that it actually scales with the area. As you increase the illumination area, then the current also increases, which tells us that it is not happening due to some local effect. Okay, the entire sample is contributing, so which is also a characteristic of bulk photovoltaic effect. Now another thing is that which is often common that it can come due to the contact. So we did a mapping of this thing, and we can see that if you take a line scan here near the contact, the current is much less. It's actually kind of negligible. So the majority of the current is coming from the sample bulk itself. So it's not a contact dependent phenomena. But there are some other things which can kind of rule out whether it is contact dependent phenomenon or not. That is the polarization dependent. So if it is due to Schottky barrier or photothermal effect, you don't see the polarization dependence of the photocurrent. However, we do see a distinct polarization dependent photocurrent in this sample. Another interesting thing is that if you increase the power density, then the short circuit current initially increases linearly and then it becomes to the power half, which is also a hallmark of the shift current based photocurrent. If it is due to a Schottky barrier, then it will be linear throughout. If it is due to say photothermal effect, then it is generally super linear at the higher power. Okay. However, this is kind of a hallmark for the Schottky for the shift current based photovoltaic effect. So we approached Srijit to kind of explain this thing. So I will not go in details into that. He used this Keldy's non-equilibrium Green's function technique. He also take into account the presence of lead and other things. So if there is no lead, if you have just the layers, he took 3 layers. If you neglect the lead, then there will be only current if you shine the light. But with the presence of lead, it can produce some current, but not too much. Okay, but if you now introduce a screw dislocation, basically a cut into it, then the current actually increases significantly. So here is the this is just 3 independent layers, the current will get this much, but in presence of light, you will get the current significantly, and it will also show this angular dependence, what we kind of qualitatively matches with the nature of what we see in our samples. So as it's a kind of you see current without applying any voltage, so we try to use them as a self-powered photo detection, and it actually works pretty well. So this is the responsivity is a function of wavelength. You do see the presence of A exciton and C exciton in the photocurrent. The on-off time is also pretty fast. It's in the hundreds of microsecond range. Okay. And we also characterize their basically noise performance, which also looks a bit promising. So these are the parameters that we observe. It's a few hundred milliampere per watt the responsivity, and detectivity in the range of 10 to the power 11. And we also back calculated the detectivity from the noise figure, which also comes in the same range. So to conclude, we successfully showed the presence of a bulk photovoltaic effect in CVD grown spiral sample. Okay, we did a thorough characterization using cross-sectional TEM, then SIG, and it tells us that okay, there might be some strain present in the sample, but that is not the whole story. Probably the broken inversion symmetry is mainly responsible for the observed photovoltaic effect, and yes, it can work as a self-powered photo detector. With this, I'd like to acknowledge many people. So these are basically only the PI's name are there. There are a lot of students from each group involved in this work, and I would like to acknowledge all of them, and definitely the funding agencies. Thank you for your.
My work is close to this one, but I just want to know this crew disclosed case on which you are saying that from mapping, or you are measuring that, like normally burger vector is there, the measurement of the screw dislocations.
Dislocations we are seeing in the cross-sectional TEM.
So they are of uniform size, because for the strain they are uniform, or because the defects need to be uniformly distributed.
It's a line defect. Okay, it originates from the center and it goes along that line. Okay, so as a result, what you see is that the layers are kind of stacked on top of another. There is no twist between the layers. Okay, if there is a twist between the layers, then you also break the rotational symmetry. Okay, that we don't see. If you break the rotational symmetry completely, then the lobe will be essentially whatever I understand is that.
It's a line.
Line defect. Yes, it's a line defect. Yeah.
So one more short question is.
How much open circuit voltage you get, and what is
we got
circuit
around
current?
100 millielectron volts, and the maximum we got is 250 millielectron volt, and the current that we observe in the range of tens of nanoampere. Yeah, in that sense it's not that much, but it's actually a bit higher compared to the other bulk photovoltaic system that people have observed in, especially in WS2 system samples.
So, at the center of your structure, what is the symmetry of the crystal? Is it 2H, 3R?
D3H. The crystal symmetry is D3H. So, it is not reducing to C3, okay, which if you break the entire symmetry, then probably it will come to the reduced symmetry state, but it is still preserving the D3H symmetry.
Okay, last question. So they are backside.
Hello, thank you for very nice talk. So I have a curiosity about the fill factor of those devices. Like I see a straight line kind of thing.
Oh,
And
okay.
Do you have any idea, like your engineering thing, how to increase the fill factor?
Fill factor. Fill factor is terrible. I think it's I'm not exactly sure, but it is probably less than even 10% or something.
Yeah. So it
Yeah,
can be
because it's not really a rectangle kind of thing. It's a triangle, because fill factor in generally bulk photovoltaic systems are pretty low, because it's kind of, you see the triangle, not a rectangular kind of thing. If it goes more towards a perfect rectangle, then you get a very high fill factor. Okay, but in this case, you'll never get that.
So you are planning to or engineering anything so that increase the fill factor?
We are rather than instead of trying to increase the fill factor, we are trying to improve the current. Okay, because increasing fill factor, there is some fundamental limitation on that. Okay, but we can try to increase the current, because voltage we are already getting pretty high. People even got up to 30 volts in some ferroelectric material. Okay, so you are trying to combining this ferroelectric layer and see if it improves at least the current to a certain extent.
Okay, let's thank Atul for excellent talk. Let's move on to our next announcement in the organization.